Hi, good morning, guys. I hope all of you are doing well. Like I texted you earlier, I might not be available for direct conversation during our session today, so I thought I'd record a little bit of the slides, and that will help you guys sort of draw the isomers for alkanes and also study on the types of carbons based on connectivity. Okay, so these are basically the slides from last time. So I'm just gonna jump into this slide where we talk about different kind of carbons based on connectivity. Actually, right before that, I want you to go over the priority table for functional groups and try to name these compounds. Okay, these three compounds. Maybe some of you have already done it, but I still want you to name these compounds. All these three compounds have different functional groups, and out of those different functional groups, one will be the main priority, which will be the suffix, the main name, and the other functional groups would be the substituent. So I want you to go to this table and see what's the suffix you use for the main functional groups, and what's the prefix that you use for the substituents. Okay, try doing these three problems, and from there let's go on to this. So as you can see here, we are focusing on these red carbons, on these four compounds, and these red carbons are different based on their connectivity. Okay, if you see the first carbon here, the carbon in the first molecule, this red carbon is connected to only one other carbon, whereas if you look at it here, this carbon is in the middle of the chain, it's connected to two other carbons. Here this carbon is connected to three other, and here four. If you have a carbon which is in turn connected to one other carbon, that's the primary carbon. Okay, first degree. This one, secondary carbon, second degree carbon, tertiary carbon, third degree carbon, quaternary carbon, fourth degree carbon. So I might use these terminologies in the future sessions, so don't be confused. Please study this first and try drawing these carbons, different kind of carbons, and see your molecules, see the molecules that you have drawn or named in the past, and see if you can classify them on the basis of connectivity. Okay, primary, secondary, tertiary, or quaternary. From there, let's go to the types of alcohols, and even the types of alcohols are based on the types of carbons the OH, the hydroxy group, is connected to. Okay, if the OH is connected to a carbon which is connected to one carbon, in other words, if the OH is connected to the primary carbon, that's called primary alcohol. If the OH is connected to secondary carbon, here, this is secondary alcohol. If the OH is connected to tertiary carbon, this is a tertiary alcohol. But we can't have quaternary alcohol, right? Because you can't have a OH that is connected to a carbon which is in turn connected to four carbons. That is not possible because carbon can't make 5 bonds, right? That would be a Texas carbon, which is a satire for Texans, I guess. So primary alcohol, secondary alcohol, tertiary alcohol. Let's do the same thing for haloalkanes. Primary haloalkanes, if you have a halogen atom that is connected to a carbon which is connected to one carbon, if you have a halogen atom connected to a carbon connected to two carbons, that's a secondary and a tertiary. So for alcohols and haloalkanes also, I might use, hey, primary alcohol, secondary alcohol, this one is a secondary haloalkane, this one is a tertiary haloalkane. So make sure you become clear on this. And all these are important. Maybe SL will not cover this. We'll cover a reaction called nucleophilic substitution reaction, where you'll have a nucleophile which is nucleus loving, the positive charge loving group, attacking a organic compound with a halogen or a hydroxy group coming out, and in the product you will see the nucleophile will get attached to the carbon, and the Br or the OH group would be removed. These types of reactions are called nucleophilic substitution reaction where a nucleophile will replace other nucleophile. And the types of alcohols or types of haloalkanes are really important while we determine the rate of this reaction. Maybe a primary alcohol will behave differently than a secondary alcohol in a nucleophilic substitution reaction. Maybe a primary alkyl halide will behave differently than a tertiary alkyl halide in a nucleophilic substitution reaction. Okay, I also want you to look at nucleophiles versus electrophiles for both HL and SL. This one, at least see what it means. Nucleophiles means nucleus loving, phile means loving, electrophile means electron loving. in order to be nucleus loving, they have to be negatively charged or excess of electrons, have excess of electrons. In order to be electrophilic, you have to be positively charged or deficient in electron. Okay, just do a little revision on this. So now let's quickly move over the idea of structural chain, structural or chain isomerism in alkane. I think I briefly mentioned to you about this last time. So alkanes, you can have the same number of carbon atoms in alkanes, but different chain structure, right? You can have a linear or branched alkane with the same number of carbon atom, and that starts from C4 onwards. Until C3, until propane, the chain isomerism is not possible because you can't branch a methane or a ethane or a propane, right? But once you go to butane, there's a possibility you can either have a linear molecule with 4 carbon or a branched molecule. And the possibility becomes more and more as you increase the number of carbon in the chain. And that isomerism, in which the molecular formula is same, but the chain structure is different, that kind of isomerism is called a structural isomerism. Alkanes distinctly so structural isomerism. And while we are going to draw the structural isomerism of alkanes, but what I want you to realize is while we study those different structure, I want you to see how their physical property changes. Physical properties like density, boiling point, how these changes. I'm going to talk about coefficient of viscosity and vapor pressure in the next lecture. Maybe I won't have time today, but how the density and the boiling point of those different isomers of alkane changes. What I'm going to tell you right now is the boiling point and this density both are related to London force, which is an intermolecular force. The intermolecular force, the London force, would increase when the contact surface area would increase. So if you have a linear alkane and an alkane with the same number of carbon, which is not linear but a branch, for linear alkane the density would be more, the boiling point would be more, the viscosity would be more, because there is more contact surface area in linear alkanes. In case of branch, the contact surface area is not as efficient, it's less, so the density and boiling point would be less. So I want you to sort of think about that as we draw the structural isomers of alkane. Okay, 4 things: density, boiling point, and viscosity are very similar. They will increase sort of linearly, and they have direct relationship with the chain structure. Vapor pressure is a little bit different. I'm going to talk about this next time, but these 3 you can sort of start looking at it right now. Okay, so difference in physical properties. These are the physical property. Why do those physical properties differ? Because the intermolecular London force is different. The van der Waals forces are different. Even more significantly, the London force is different because these are non-polar molecules. So we talk about London force and not that much of van der Waals force. Okay, so linear the molecule, more is the contact surface area, more is the London force. Branch the molecule, less is the contact surface area, less is the London force, and less is the density, and less is the boiling point, and less is the viscosity of the molecule. Okay, so yeah, let's get started with butane. So this is the butane molecule, line structure, C4, 1, 2, 3, 4, all carbons arranged linearly, and this is called butane or N-butane, N standing for normal, straight. But what you can also do is remove 1 carbon and draw a 3 carbon molecule and put that terminal carbon on top here, attached to the second carbon. If you look at the molecular formula, this will also be C4H10, but the structural formula is different, so it's not N-butane anymore. This is called, of course, the IUPAC naming, you should know this by so far, 2-methyl propane. The methyl is coming off of the second carbon, so it will be 2-methyl. Propane is the longest chain. Or we also call this isobutane, because if you look at the groups around this central carbon, they are identical. All methyl groups, that's why it's called iso. Iso meaning same. Isobutane. Okay, so there are 2 isomers, the chain isomers in alkane, in butane, N-butane and 2-methylpropane or isobutane. Which one do you think will have higher boiling point, higher viscosity, higher density? The N-butane, because of the linear structure, more contact surface area between molecules of N-butane, more intermolecular London force, more is the boiling point, density, and viscosity. Okay, So I want you to draw the same for pentane. What I'm going to do is I'm going to get you started on pentane, and for hexane and heptane I want you to do it yourself. Okay, so let's see if I can help you on